Alright, class. So now that we are done with the 2D heat transfer problem, we're gonna move on to the 2D linear elasticity problem. As always, as you can expect, we're gonna start with the strong form of the linear elasticity problem, and it's gonna be very similar to the strong form of the heat transfer problem. The only difference really is that there's now x and y components. So when we are trying to solve the linear elasticity problem, we want to solve for the displacements at the nodes, and there's an x and a y component of the displacement. So this is, in a way, two heat transfer problems combined. So what you can see here is this, if you remember the heat transfer problem, looks something like this. Let me just write it here for a sec. Remember heat transfer. So in the heat transfer strong form, what we had was the divergence of the heat flux plus some source term equals 0. That's what we had for heat transfer. So in this case, we have two heat transfer problems. It's not heat transfer, but the form is the same. So divergence of some vector field plus some scalar field equals 0. Divergence of another vector field plus some scalar field equals 0 on omega. And the difference being here that the flux is what we had before was the heat flux. Here, this sigma x, you can think of that as flux of linear momentum. And then this, what was a heat source term in the heat transfer problem, is going to be a body source, source of linear momentum called a body force. And there's a constitutive relation also, if you remember the way we had defined this flux of Q. In this case, we are going to have sigma x and sigma y, these sort of linear momentum fluxes, are you can put them in this matrix, which is the stress matrix, and you can relate that to the gradient of the temperature. And what is the equivalent thing that we had in the heat transfer problem? We had Q was minus the gradient of the temperature. So in a way, hopefully that helps you see that these two equations right here is sort of like the heat transfer problem. This is also like the Fourier law for heat transfer. And then we have boundary conditions. We have essential and natural boundary condition. As you can imagine, if you have displacements prescribed on the boundary, that's an essential boundary condition. Also called Dirichlet boundary condition or displacement boundary condition. And this is a natural boundary condition, also called traction boundary condition or Neumann boundary condition. Again, so we have somewhat of a similar setup as before. The strong form is to solve a PDE over some domain omega that has boundaries, and there's two portions of the boundary. There's a portion of the boundary which is TU, which is part of the boundary where we have prescribed displacements, U equals U bar on this part of the boundary. And then we have another part of the boundary where we have prescribed tractions or forces. The correct term is tractions, but you can loosely think of that as forces. So this other part of the boundary that we're going to call gamma t, which is part of the boundary. And in that one, we have prescribed tractions, check forces per unit area. And then those are the boundary conditions in the domain. And then what we have to satisfy is these two equations, which are basically going to give us the force balance inside of the domain. And this is the constitutive equation. So this is, you can think of this as force balance. It's not exactly called force balance, but it's you can think of those two as force balance, and this is Hooke's law, and it's basically the constitutive equation relating the displacements to the stresses. So that's the strong form. Also, a few other notation that you might have seen in your 323 class. This matrix sigma has 4 components. So this will be sigma x, tau xy. This is a symmetric matrix. So there's normal stresses and shear stresses. This column right here, that one is the vector sigma x, and this other column right here is the other traction sigma y that are identified here. And then this gradient of u, that is the strain actually. So and that one has also symmetric and has these different components. We have the normal strains, epsilon x and epsilon y, and then the shear strain. And then this matrix D right here, that one has the material properties. I will need an extra page. So the matrix D in sigma equals D gradient U. So this one is basically the material properties. And we're gonna define it later on. The only thing that you should know is that it depends on the parameters that define the material. So for Hooke's law, you would have, or generalized Hooke's law, you would have Young's modulus and Poisson ratio. And as I said, the specific form of the D, I'll introduce that later. But for now, just enough to clarify that it's a function of the material parameters. So you should have Young's modulus and Poisson ratio in there. One extra thing that I would like to point out is that writing the solution of the linear elasticity problem as the solution of these two problems is nice in the sense that it looks very similar to the heat transfer problem, but the more common way of finding this problem, more common way of finding the linear elasticity problem is, instead of two equations, you only have one equation. You have the divergence of the entire stress matrix plus a vector of body forces equals the zero vector. So instead of having, for x, this, you can think of this as equilibrium in x, equilibrium in y. So instead of having these two equilibrium, you can just have a single equation. So this is both x and y combined, and the rest is the same. So sigma is still related to the strain, which is the gradient of the displacements, and you still have some tractions on some part of the boundary, and you have some displacements on another part of the boundary. So really the only difference that I had was I combined these two into a single one. So that's the definition of the strong form. And then you would have to solve this with the finite element method, as we have done for every part of this class, what we did for 1D, then what we did for the heat transfer problem. We have the strong form, we have to turn it into the weak form. So that's the next goal, but before I get there, I'm gonna actually do a couple of things. So I'm not gonna do the whole derivation. I think you can go back to what we have done for the heat transfer problem, and you can also go to the book to see the full derivation, but I'm gonna sketch out a little bit of the steps that you should take. Spoiler alert, is gonna be the same as you've done before, so multiply by a weight function, integrate over the domain, make that equal to 0, do integration by parts, or in this case Green's formula, which is sort of the integration by parts for 2D, and then you're gonna end up with some integral form. But there is just one subtle difference, which is that in this case, as I said, and this is the main difference between the heat transfer problem and the linear elasticity problem, is that you have two components, so you have ux and uy for the displacements. And similarly, when you think about your weighting function, you should think of a vector of weighting functions with two components, wx and wy. And so what you can think of doing is following the heat transfer problem, but independently for these two, and then combine those two into a single weak form. So what you can do is, for momentum balance in X, you would have integral of this times the weighting function. So I'll let you go back and check what this was, but so I'm gonna have the weighting function x times the divergence of this vector sigma x plus bx equals 0 over the domain. So I multiply by the wave function and integrate, but now I have two equations. So for momentum balance in y, I'm going to end up with integral over the domain omega y of divergence of sigma y plus by equals 0. So this is similar to the heat transfer problem, just times 2. One for the x component, one for the y component. So at this point it looks the same. So multiply by wave function in integrate. Just make a little bit of then use Green's formula, which is the equivalent of integration by parts for 2D. So what you're gonna end up doing is, if you use Green's formula, I'm just gonna skip through it, but you're gonna end up with, you're gonna pass basically this gradient to the, from the sigma x, you're gonna pass it to the wx. So I'm gonna end up with the gradient of wx dotted with the sigma x vector plus the integral over the boundary of wx times the x component of the traction over the boundary, and only the part of the boundary with natural boundary conditions survives, because the part of the boundary where we have displacements, as always, the weighting function is going to be 0 for that part of the boundary. So only the boundary with natural boundary conditions remains. and then integral over omega of wx bx equals 0. So that's what I get from using Green's formula on the x component. And then if I use Green's formula on this component, then what I'm going to end up with is very similar. It's going to be gradient of omega y times the sigma y, which is the traction in the y component, so it has a shear and a normal component, plus integral over the natural boundary omega y ty d gamma plus integral over the domain omega y by equals 0. And then if you sum these two and rearrange a little, then you're actually going to get to the weak form. And this is what I have here. So the weak form is find u in the space u, and let me just define the space u is going to be functions u in C0 with u equals u bar on gamma u, such that the gradient of w times the d, which is the material properties, times the gradient of u, integral of that over the domain equals the integral over the natural boundary, or the part of the boundary with natural boundary conditions, weighting functions times the tractions imposed at the boundary, plus integral over the domain of the weighting function times the body force vector for all w's in the space u0, where u0, actually here it is defined. Here it says h1. You can think of h1 and c0 as more or less the same. It's not exactly the same, but for this class we won't really cover the difference. You can think of h1 and c0 as being somewhat the same. And w is also belongs to c1 or c0 with w equals 0 on the part of the boundary that has essential boundary conditions. So to recap this part of the lecture, and this is the only part, I'm going to stop here and I'm going to upload a different video for the rest of the lecture. But to recap, we have the strong form of linear elasticity, which looks like the heat transfer problem, with the difference being that we have sort of two problems at the same time, because we have displacements which have x and y components, and we have forces which have x and y components, or tractions which have x and y components. So you can think of the linear elasticity problem as being the combination of these two problems, the momentum balance in x, momentum balance in y. Again, similar to the heat transfer problem. You have a constitutive equation that relates the stresses to some derivative of the displacements, and you have boundary conditions, which can be natural boundary conditions, meaning you impose the traction that's equivalent to the normal component of the stress, and you have essential boundary conditions, which means you impose the displacement. Then I'm going to skip a little bit of the other things that I said. The other important thing is that in some cases, I think what you'll see more frequently, not in some cases, I think what you'll see more frequently is this form. So instead of seeing it as two separate problems, more likely you will see it as a single problem. Divergence of sigma plus b equals 0. In order to go from the strong form to the weak form, we're going to go the same way that we've done for the 1D problems and for the heat transfer problem in 2D. We're going to multiply by a weight function. We're going to do integration by parts, or Green's formula in 2D, and then rearrange a little bit, apply boundary conditions, and we're going to end up with our weak form. Again, what is the difference? The difference being that to get to the weak form, we have now, because we have 2 degrees of freedom, displacement in x and displacement in y, we also need to introduce two weighting functions. We have wx and wy. And so what you can do to get the final weak form is multiply by the wave function x and integrate the x equation, multiply by the wave function y and integrate and make equal to 0 for the y equation. Then you can use Green's formula independently on each of these, and you're gonna end up with these two equations right here. Again, you can go through the details on your own, but hopefully the main idea is clear. Multiply by wave functions, do integration by parts. And in this case, you can combine both equations to get a single nice looking equation, which is the weak formula that we're going to use. And it has the same structure as the heat transfer problem. So if you remember the heat transfer problem, again, let me do a note here. So for the heat transfer problem, what we ended up with was integral over the domain of gradient of W times D times gradient of temperature. The only difference was that in the heat transfer problem, the W was a scalar. Here it is a vector. Also in the heat transfer problem, we had this minus sign because of the flux was the negative of the gradient. And we had the last one was like this. So if you remember, the heat transfer problem looked like this. So it looked very similar. The difference being in the heat transfer problem, this was a scalar, 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 scalar. Here it's a vector, vectors, vectors. So that's because there's an x and a y component. Vectors. All right, so I'm gonna stop right here, and then I'm gonna go over some of the implications of this weak form for the stiffness matrix